So next we're going to talk about outliers and how what methods we can use to identify outliers. You should probably already realize we have discussed quite a few methods that we can use to detect outliers in a dataset. And chapter 12 will provide you a more in-depth discussion of outliers because they're most of times I think we're aware of the most simplest form of outlier, which is context-free. It's global. It's just an outlier no matter what the context is. But there are lots of other outliers that we're going to cover. Lots of other types of outliers we're going to cover in chapter 12. So far what we have learned to detect outliers, we can use box plots, right? We can use histogram analysis. We could have a histogram and then a very stretched out values far apart from the central values. So histogram can also be used to detect outliers. Regression, so using linear regression, for example, data points as far away from the regression line could be taken as outliers. Clustering, we just saw an example of that. Points as far away from all the other clusters are possibly the outliers. So that's all we're going to talk about today, and more will be discussed in chapter 12. And next, we're going to talk about data redundancy. So as we mentioned earlier, data redundancy happens, well, it happens in one data set as well if you're not be careful when you collect the data. But most often, data redundancy occurs when you have data integrated from multiple sources. When you integrate data from multiple sources into one coherent data set, you could also encounter other issues. For example, if you have data from different databases, then you need to integrate the database schema. In one database, customer ID could be a customer ID. In another database, customer ID is customer number. So you need to carefully examine the data dictionary comes with the data bases and try to either create crosswalk among those attributes or come up with more sophisticated way to convert data. As I mentioned earlier, data integration is one active research area. Machine learning and other methods has been applied. The more data sources that you need to integrate, the more challenging the task can be because there's just a lot of variations, lots of unexpectedness in different data sets. And when you have data sources, multiple data sources, you probably also going to encounter issues like data value conflicts. So, for example, my salary in this database is different from my salary in another database, and the scale could be different. For example, lots of measurements can be done in metric system. It could also use British unit, right? So those are all differences that need to be resolved before we can actually perform meaningful analysis. Here in this part, we're going to focus on the data redundancy problem. One challenging problem is entity and identification problem. This is not just in data mining, it very broadly in information management, in information retrieval, question answering systems, all kinds of things that has to do with recorded information. We have this issue. The issue is the same real-world entities can be labeled, use different names. Bill Clinton, William Clinton, everybody's name can be spelled in different ways using including or not including middle name, put the first name first or the last name first. There's so much variation. And there are also synonyms and all that, customer ID and customer number being one example too. So that is very challenging. It's an active research area, how to map those varying things into a controlled vocabulary. And that is not what we're going to discuss today because you probably need a class to cover all of that. What we're going to cover today is that specific kind of redundancy that we can fairly easily detect is naming differences and derived data. So if two attributes are the same, they only been given different names, their values are quite clean, then we can expect the values are very similar. We can use correlation analysis to identify those attributes. So the two attributes are exactly the same, have same set of values, only they have different names. Okay, so that can be easily identified. Derivable data may also be redundant. For example, the total price, you already have a column called total price, and then you have another column called sales text. If you're analyzing data from one state, you probably have, again, highly correlated data because sales tax is just 8% of the total price, for example. So those redundant data attributes does not offer any new information to a mining problem. Therefore, they should be removed because having them increase the dimensionality and creates unnecessary computation. So we want to detect them and remove them. When we have nominal data, we can use Chi-square test to identify attributes that are highly correlated. So Chi-square test a correlation between two nominal attributes. So the idea is, if we assume, in this case, two variables, right, play chess, whether this person play chess or not, whether this person like science fiction or not. So if we have a data collection and we can create a contingency table like this to count how many people, how many 250 individuals play chess and also like science fiction. 200 individuals like science fiction but does not play chess. So we put the counts into a table like this. This would allow us to perform chi-square analysis. So the idea behind chi-square analysis is, if play chess and like science fiction are independent, are two independent variables, then the expected co-occurrence of for an individual to play chess and like science would be total number of samples that we have times the probability for one person to play chess and times the probability for one person to like science fiction, right? Assuming those two variables are independent, their joint probability is just a simple product of the two individual probabilities, marginal probability, right? So given this, we can use, this translates directly to this. The count of A1, how like science fiction, how many people total in this data set like science fiction, and count of B, B1 in this case, how many people in total in this data set like to play chess. Okay, so this will give us the expected value for anyone who would play chess and like science fiction. So this would be the expected value that we have computed, and put it here. So for each data cell, using the same formula, we can compute the expected value. Once we have the expected value computed for each of the data cell, we will be able to use chi-square test, chi-square statistic to test the correlation. Chi-square statistic is defined in the following way. Basically, what you see here is, so R represents rows and C represents columns. So this formula tells us we're going to find the squared difference between observed value, O, ij, the difference between the observed value and the expected value. And we're going to divide or normalize that using the expected value, and we will add all those individual differences together. So intuitively, you can see that the further away observed value is from the expected value, the greater chi-square is. Okay. This means the expected value was computed under the assumption that two variables were independent. If our observation is far away from this independent assumption, then that says our data are correlated. So therefore, the larger the chi-square value, the more likely the two categorical nominal data are related, right? And then we have a chi-square table, just like we have a z-score table, for us to find either the critical value of the chi-square distribution or the probability for us to observe this chi-square statistic. And when we use chi-square test, the table will be formulated in a way that the chi-square value is going to be given based on the degree of freedom. For chi-square test, because we have rows and columns, the degree of freedom is the number of rows minus 1 times the number of columns minus 1. So we're going to look at one example. So now using the same example from the last slide, our null hypothesis is a variable A. So this, let's see, this is A, like or not like science fiction. This is a variable B, it's a binary variable, right? Like or not like play chess. And we want our test significance to be 0.001. This is very restricted. So we use the same formula, calculated the expected value, and then we're going to compute the chi-square value by summing up the squared difference divided by the expected value in each of the data cells that we have. We obtained a chi-square value of 507. Using the chi-square table, we can find, in this case, because we have degree of freedom is 1, because this is 2 minus 1 times 2 minus 1. So we have a degree of freedom of 1, and our test significance is 0.001. Therefore, chi-square critical value should be 10.8. Any value greater than 10.8 would suggest the variables were correlated. So using critical value is one way to tell whether the two categorical are correlated. If it's really highly correlated, then we don't need both variables in the data set. We can remove one of the two, any one of the two. When we don't use the table, we could for example, using R, most of the test method function will give you a p-value, which basically means if what's the probability for you to see a chi-square value to be 507. If the p-value is smaller than your alpha, then you can reject the null hypothesis. So it's just a critical value and a p-value are just two different ways to help you to make a decision on whether you can accept or reject the null hypothesis. So we look at Chi-square as one way to compute the correlation between two categorical or nominal attributes. For numerical data, we can use correlation coefficient, Pearson's test, to find linear correlation between two variables. Pearson's correlation coefficient is computed using this formula. An intuitive reading of this formula shows that these are going to be a positive value when A and B are increasing at the same time and decreasing at the same time, so that this top, the sum, going to be a positive value. Otherwise, if A is increasing at the same time, B is decreasing, you're going to have a negative numerator. Therefore, your R value is going to be negative. And you probably also observe that this is standard deviation, and this term give you the normalized z-score normalization. So this normalization using the deviation will normalize the R, the coefficient, and make it take a value between -1 and a +1. Okay. So if between two numerical variables that you found the correlation to be between 1 and 0, then A and B are positively linearly correlated. The higher, the stronger the correlation. If R is 0, then it's not linearly correlated. It may still be associated in some other ways. If R is less than 0, then those two variables are negatively linearly correlated. So when one value is increasing, the other value is decreasing. This set of graphs to show you the visual presumption when you actually plot two variables with different correlation. So this shows all the data points, the scatter plot, right? Those two variables on two axes. If you have those, all the data points falling on a strict line, you have a negative correlation of 1. If this line forms in another direction, then you have a positive correlation of 1. The greater the value, the greater one value, the greater the other value. In between values, you will see the pattern reduce. The line becomes thicker and thicker, and to the point that you don't actually see a line. It's just a random data points, forms almost a circle. It could also be a square. Basically, you don't see a tendency, a line there that you can fit that doesn't have lots of residuals. This gave you some visual appreciation of the linear correlation. When we talk about Pearson's coefficient, we should probably also mention a related measure, covariance. Covariance, as you can see, is very, very similar to correlation. The only difference is this value is not normalized using the deviation. Therefore, this value it does not have an upper bound. It does not have a lower bound. It can be positively infinite or negative infinite. But again, the interpretation is very similar. If the covariance is greater than 0, then A and B both tend to be larger at the same time. So we will see those we have a positive correlation. If the covariance is less than 0, then we have a negative covariance. In practice, to examine, compare a correlation, we always use Pearson because it's normalized. We can compare if the correlation of two variables is 0.8 and the correlation of another variable is 0.5, then we know that the first one has stronger correlation. Covariance, because it's not normalized, we don't know how large is really large. But it is absolutely useful in other statistical analysis. For example, principal component analysis that we're going to study shortly. So covariance, also provide an example here. We have the formula, which is this, and we can rewrite this. If we do a little bit of math manipulation, it's equal to that. So therefore, we can have a simplified covariance calculation formula. So we have the example have two stocks and they have different prices. In 1 week, we want to see whether the price fluctuation of these two stocks are somehow correlated. Are they rise or fall together? So we first compute the average of A, so E for expected value, which is basically the average. Average of A, and now we can take this, and average of B is that, and we follow this formula. This again is a dot product, right? So we did dot product, and then take the average of the dot product and then minus the product of those two values. We got 4. So it's positive. We know those A and B rise together, but we don't really know how strong that is. We know that 4 is probably stronger than 1. But if we have a different data set and we have different two variables and we have those correlation to be 10, do we know that 10 is greater than 4? Indicates that the correlation over there is greater than the correlation over here. No, we can't. They're not comparable because they're not normalized. Okay, so this concludes our discussion on data redundancy detection. So here basically we talked about two ways to detect a correlation. One is for categorical value, another is for numerical values. Next, we're going to talk about dimensionality reduction in a different video.